Fan was not there, no? Fan கூடவா?
So very good morning all. Am I audible?
Yes, sir, you're audible.
Yeah. So we can start by 11:30. Will that be fine? So I'm just waiting for some more participants to join. Once they join, then by 11:30 we can start. Yeah, Satish has joined. So is the content visible? I hope it is visible to all the people, right?
Yes, sir. It's clear.
Yeah, fine. That's fine. So a very warm good morning to one and all present here. Participants, we welcome on the behalf of Department of Civil Engineering, on behalf of external expert, Professor Hadas, and then Dr. Ram. We welcome you all for the first GIAN course on nanomaterials for water treatment. Due to the inaugural delay, we are starting the session by 11:30. So, and then this course, as you have gone through the lectures that have been planned, it has been planned in such a way that in order to get the maximum uh, uh, exposure of how these nanoparticles are used in different streams, or otherwise the domains. So, be it the water, be it the wastewater, or the applications of nanomaterial with respect to the other processes, how efficient are they, and then what are the targets that the nanoparticles can aim for, because the nanomaterials or the nanoparticles are now being used vastly. Even nanomedicine, we are using these nanoparticles to target specific cells which needs to be cured. So moving on, this first lecture would be giving a basic understanding about the nanomaterials, where it started, and then what are its different synthesis rules and characterization techniques, the mostly commonly used or adopted techniques with respect to the nanomaterials. So moving on, the outline of the course would be an introduction about this nanomaterials, the history behind it, the types of nanomaterials, the classification, and then how do we classify and what basis do we classify, synthesis of nanomaterials, and characterization techniques. So with respect to nanomaterials as well as the characterization techniques, there are different techniques, but we will be looking one by one in detail. So coming back to the introduction part, as all we know that these nanoparticles or nanomaterials, so we will just look into the nanoparticles in later course of time. But the nanomaterials as a material with any external dimension in the nanoscale range. So in 10 to, if you say it as 10 power minus 9, we used to say that, or any of its internal structure or the surface structure in a nanoscale level. So this we say it as a nanomaterial, and nanoparticles or as an object with all the three external dimensions in the nanoscale level, or at least two dimensions will be there in the nanoscale level. So these nanomaterials and nanoparticles, as you all know, because most of the audience are from faculty as well as research scholars, these nanoparticles have been used widely due to its properties. So one is the very large surface area it possesses, and then the optical properties. It behaves differently with respect to different range of light when it is passed upon. The magnetic and electrical properties helps them to get attention not only with respect to water treatment, but with respect to the other domains of engineering as well as sciences. And then previously in the era where the nanoparticles was not being used widely, so there was a rate at which the invention or otherwise the process efficiency was very less. But when the advent of nanoparticles came, and then it opened a plethora of options to the researchers in order to explore their applications in different domains. So first the nanomaterials was made, nanoparticles, and then in that there are different particles, be it the carbon nanoparticles or graphene or metal oxide nanoparticles for various applications. Nanocomposites, we have gone for two different types of nanomaterial to form a composite so that it can target the specific contaminant or pollutant, be it in water or wastewater. So myself, I'm from an environmental engineering background. So whatever the example I give might be from water and wastewater. But these nanoparticles or nanomaterials have made the appliances or the consumer products in a very big way, in such a way that this has reduced the size of most of the electronic appliances that we use. So this is not only related or not only focused much about with respect to the environment, but also the other domains of engineering has also yielded its results, or has got its own share. So how big are these nanoparticles? So that is one such thing. So if you look at these nanoparticles, it can be our hair. Our hair is something around 50,000 to 10,000 nanometer wide. And then if you take a pinhead, it is 1 million nanometer wide. And then if you take a sheet of A4 size paper, which we normally use for printing, it is around 75,000 nanometers thick. But when we synthesize the nanoparticles, we talk about in the range of 1 to 100 or size specific nanoparticle synthesis, or otherwise shape specific nanoparticle synthesis have been taken up in order to target the contaminant or pollutants. So again, with respect to the RBC, the red bed corpuscles, it is something around 7,000 nanometer wide. If you look at the big chart, so we are talking something in the range of nanos, or 10 power minus 9, where the DNA, so something around our DNA stands about some 7 nanometer long. And then even in the atom sites, quantum dots, then less than 10 or less than between 1 to 10, we talk about the quantum dots, which is not our synthesis matter of concern. But when it looks about the filtration techniques, before it was as delivered in the presidential address as well. So before it was, when you look about the water treatment, the conventional treatment, it had sand filtration, slow sand filtration, rapid sand filtration, where the rate at which the filtration happens, though the rate at which the filtration is slow, but still it will yield a very high quality water with respect to the pathogens, especially the pollutants or the pathogens, microbial pathogens or pollutants. So those were it all depends upon how these voids, what is the void space that it has, so the water percolates down the slow sand filter, and then it reaches it gets a very high quality water. And then when it goes to the micro scale, again, macro size, then microfiltration, ultrafiltration, then nanofiltration. So again, there are steps, and then the micron size, 10 power minus 3 to 10 power minus 6, where you have all the pathogens, be it the virus, be it the bacteria, all falls in place, and then colloids. So one such big thing that in water, to remove the colloidal suspension. So again, you need to have a very transparent or crystal clear water. So again, removal of colloids also falls in this. And then comes the nano range, so 10 power minus 6, and then in that the colloids are also there, and then bacteria, virus, and then 10 power minus 9 we talk about, or otherwise the nanoparticles are of the area of concern. So when you date back, these nanoparticles have been recently used, or otherwise recently fabricated or synthesized in various things, but at the age-old time also, these nanoparticles have been used. Lycurgus cup made by Romanians in the year 400 AD is nothing but a glass that changes its color when the light is passed upon. As I have said that these nanoparticles, this is one such property that the nanoparticle exhibits, so that it is being preferred in various domains. So the glass is composed of gold and silver alloyed nanoparticles. And then when we talk about silver, silver is one such, silver nanoparticles or silver metal is one such agent that has been used widely for its antibacterial property since its ages. So gold combined with silver alloy nanoparticles were used or coated onto the surface, so that whenever you pass the light, when the glass looks green in reflected light, but when the light passes through the cup, it has its red color. So this is one such property. As I have said, that the first property of nanoparticle is because of its huge surface area that it possesses. Then comes the optical properties. Then again, the other thing is that corrosion resistant azure pigment, Maya blue, we used to say that. It was first produced in AD 800, discovered by the pre-Columbian Mayan city. So this is one such pigment that is used for painting. So again, it is a complex material containing clay with nanopores into which indigo dye was combined chemically to create an environmentally stable pigment. So these clay particles, along with the very minute clay particles, along mixed with the indigo dye. Indigo dye is also one such very old dye that has been used for dyeing, not only during the British era, but again in the in a very old age also, indigo dye is one such dye that has been used vastly. So this nanopores has been used in these dyes so that it remains intact till this point of time. So the first scientific report, because of the Industrial Revolution, on the basis of the first scientific reports in 1857, the first synthesis of colloidal solution of gold nanoparticles, that the Michael Faraday conveyed it as activated gold. So that what is activated gold? Why it is called activated gold? So it is, though its properties or the particles are of very fine in nature, but still it can do a vast thing. So gold reduced in exceedingly fine particles was its statement at the Royal Society of London when he delivered his lecture. Early in 1980s, silica nanoparticles were made as a substitute for the ultrafine carbon black for rubber reinforcements. That is one such thing, adaptability. And then in 1959, Fenhen, there is a plenty of room at the bottom. So that means that still in the late 1960s or 70s also, there was very less attention that was also sought upon at the bottom of the pyramid. So that means that even at the small details, many things got missed. So that is what it means, that there is a plenty of room at the bottom, and then the world started exploring it in a vast manner. So history, when it comes to the nanotechnology or nano term, the first person to formulate this term is from Japan, a scientist named Norio Taniguchi. And then according to Norio Taniguchi, nanotechnology mainly consists of processing, separation, consolidation, and deformation of materials by one atom or another molecule. So either you can, so he was talking about the atoms or the molecules in the one by one. So how you arrange the atoms, or how you arrange, whichever the way that you want to arrange is one such major thing that was the challenge. And then how do you process them or fabricate them, synthesis them, and then consolidate, and then deform again back them according to your own wish. But until when he first dictated the term of nanotechnology in the late 1970s or 80s, it was not a very familiar term until unless this gentleman, Eric Drexler, unknowingly used this term as nanotechnology in his book in 1981. Until then, this nanotechnology was not having a big attention over the years. And then in his book, Engines of Creation, the coming era of nanotechnology. So this is where people started looking nanotechnology as a vast option for their research problems. So he had a view about molecular nanotechnology design using bottom-up approach for fabrication of products with increases molecular control. So molecular control in the sense that how these molecules are arranged, the manner in which you want, not the manner in which they are available in the natural form. So this was one such thing that was triggering everyone to look into or jump into this nanotechnology field and explore in a very vast manner, So when it comes to types of nanomaterials, so now we have both the historic relationship of how these nanomaterials were used in the very ancient times, as well as in the after the Industrial Revolution. So types of nanomaterials. So these nanomaterials can be put together in one or the other form as natural. So which is nothing but, as the name itself suggests, that it is naturally available nanomaterials in the environment. Engineered nanomaterials, as the term itself replicates that engineered. So something has been fine-tuned. What kind of fine-tuning? So it is nothing but the molecules or the atoms have been arranged in the manner that we want. The area that how much area that we can get over this nanoparticle, or shape specific, size specific. When it comes to shape specific, be it the nano rods, nano tubes, or spheres, what kind of shape that you want. And size specific, what I mean is that between 10 to 20 nanometer size range of material can be synthesized. And incidental nanoparticles or nanomaterials, these comes out of one or the other process accidentally. So this is what it means with respect to incidental. So on the image on the right, you can able to see that. So the naturally available nanoparticles or the nanomaterials in the environment, it can be from oceans, be it the water droplets, aerosols, which travels a very vast distance. They are very minute in nature. And then these aerosols are now considered to be one such playing a big role in the climate change. And volcanic ash, where the volcano chews out the very fine-tuned ash into the atmosphere, where it can be seen even after even farthest distance here than 20 kilometers, 25 kilometers. Lightning, flash pyrolysis, though this condition is very rare, but still it generates naturally available nanomaterials into the environment. and then humic substances, biomolecule viruses, which are naturally available, nanoparticles by microbes, even the microbial population also uh, leaves nanoparticles upon in the environment. And then with respect to the other thing that is engineered, as I have said, that we fine tune the nanomaterials, the previously available nanomaterials which are there, be it organic or inorganic. Again, you can dope them, you can cover their surface in order to not to have the particles getting aggregated. You need to behave the nanomaterials engineered in the sense that these nanomaterials needs to behave differently for different environments. At one place, you need aggregation needs to happen. At the other place, you should not have aggregates that should aggregation should not happen. So again, when it comes to engineered nanomaterials, ceramic nanomaterials, metal nanomaterials, and metal oxide nanomaterials are two different things. And then carbon nanoparticles, graphene oxide are some of the recent developments that has come in the area of nanotechnology, where it has been widely used in different sectors. So one such example where I gave you silver nanoparticles for antibacterial properties. These silver nanoparticles have been used widely onto the shirts, collars, socks, even the washing machines now we have. If you keenly notice them, excuse me, even if you notice them, the detergent that we use, or otherwise the washing machine itself adds upon some silver nanoparticles into it, so that all the pathogens in your dresses gets killed. So these nanoparticles are being added, or otherwise are available in different consumer products in our day-to-day life. Personal care products. When it comes to personal care products, the sun lotion, sunscreens, again, the one such ingestion way, or one such pathway for these nanoparticles. Again, it is again one such debatable thing whether the nanoparticles can block the pores that we have it on to the skin. Again, laundry, the electronics, as I had mentioned, that the nanotechnology has shaped up the electronic industry in a very different manner. Before, we used to have everything in a big thing, but now it is everything small is now the trend. And then solar cells. Now this nano material, because of its properties, it has been extensively explored on solar cells, solar photovoltaic cells, the application of nanoparticles, and then how to increase their efficiency. And then paints and pigments. So incidental, these paints and pigments, sometimes titanium oxide, titanium dioxide nanoparticles are also being used in paints and pigments. And incidental, whenever there are any reaction that happens, you kickstart your automobile, so where you have gaseous pollutant coming in, at the same time you have gaseous pollutant, and the exhaust you will be having a layer of fine-tuned particles that get settled onto the exhaust. So that is nothing but the carbon soot, we call it as. Even this carbon soot had a very big implication in London at one point of time in late 1800s, where the London city were keep on burning the carbon as a fuel, that is nothing, coal as a fuel, and then because of this carbon soot, they could not able to have a proper visibility. So again, this can be one such thing that can be very dangerous to the environment. And then later there was several legislation to keep check about the pollution that comes out from the industry. So again, this is one such example where I gave you as incidental nanomaterials is nothing but the carbon soot that comes out. And then even with respect to Indian case, authorities, if you have recently looked upon the, or otherwise in the past 2-3 years before, the government of Uttar Pradesh has banned all the industries which are in and around the Taj Mahal, so that the marble doesn't change its color. So again, because of this carbon, or otherwise the very tiny particles that are being left into the environment, so they can play a vital role with respect to the monuments. So we can classify natural, engineered, and incidental. So we will not be covering, or otherwise we will not be having much look about the natural, but we will be looking much more into the engineered nanomaterials. So as I have already said that these nanomaterials are naturally occurring nanomaterials in the Earth's crust, generally formed through different geochemical processes. So it can be with respect to different processes that happens in the Earth's crust. 1,000 megatons of natural nanomaterials of size range between 1 to 1,000 nanometers cycle around the Earth every year. This has been from a recently available study that says that 1,000 megatons of naturally mainly from the volcanic ash or from the ocean, because of the very tiny aerosols that comes into picture. So again, 1 to 1000 nanometers of size range, they they circle around the Earth each year. And then naturally available nanomaterials vary widely in their composition, covering organic, inorganic forms and their morphology. It's not the morphology that we expect. And then the 342 megaton per year is the flux of natural available nanomaterials to the Earth's atmosphere. So that is that much amount of naturally available material is already there in the atmosphere. So natural chemical weathering process, one volcanic eruptions, lightning, metal and metal oxide nanomaterials formed by biotic, natural living organism as well as non-living organisms can yield these nanomaterials into the environment. So again, moving on, engineered nanomaterials, as I have clearly said that these engineered nanomaterials had its application in different walks of life, be it the food, be it the water, be it the energy. So energy, you can relate to solar photovoltaics, be it the water, the course itself is one such example, be it the food. Okay, food wrappers using, or otherwise silver wrappers onto the layer of the food. That is one such way where you protect your food or otherwise the food traceable material from not getting decayed. So again, this has been widely used as mentioned earlier, specifically designed and deliberately synthesized by human beings for their purpose, for their need. So for based upon their specific need, this has been having the nanomaterials are controlled based upon their size, shape and composition. Composition you can just relate with respect to the composite material, that if you want one single material, no, if you want to go with two different materials, then you can go for nano composites. So the most commonly available engineered nanomaterials are nothing but metal oxides. So example, titanium dioxide, so iron and aluminum oxide, zinc oxide, copper oxide, manganese. And then when it comes to metal oxide, these are the most dominant nanomaterials. But when it comes to nanomaterials as a whole or nanoparticles as a whole, the first place goes to silver, followed by carbon, then comes all the metal oxide nanoparticles. Silver because of its antibacterial property. Carbon, it has been widely explored, carbon nanotubes, nanorod, spheres. Now quantum dots has also been explored. Used in buildings, electronic items, computer, pharmaceutical and medical industries, and manufactured in very large quantities. So each and every year, this the quantity of nanoparticle generation keeps on increasing because of its various application in different walks of life. So incidental nanomaterials, I will not touch much, but it's a byproduct of human activities. Generally, it doesn't have any size regulation. So it comes in different size ranges, have poorly controlled size and shapes. Many of the processes that generate incidental nanoparticles are common every day. That is nothing but running diesel engines, large scale mining is one such major thing of nanomaterials getting into the environment. And then even starting a fire because of the soot that is coming out from the fire. So this image will tell you what are the different nanomaterials that are available in the market, or otherwise used in the market. This is being used. Again, it can be used in different products. So as I have already said that silver, when it comes to metal, silver predominates because of its antibacterial properties. Titanium dioxide being used extensively with respect to AOP process, that is advanced oxidation process. With the help of sunlight, you generate hydroxyl radicals and then you degrade the pollutant, contaminant, and then you get a very good quality water, especially the textile dyes, pigments, and then titanium, zinc oxide, copper oxide, gold is also being used. With respect to carbonaceous nanomaterials, carbon followed by CNT carbon nanotubes, fullerene, and graphene. So again, graphene is now picking up, but still carbon has been extensively used. Apart from that, silicon, mostly in the semiconductor industry where the silicon has been used, and other type of nanoparticle. So as mentioned earlier, this is one such picture where it will tell you the nanomaterials applications in different sectors of engineering as well as science domains, be it the research, be it the industrial application, be it the domestic application, be it name it, whatever the technology that comes in, it might be having its hold on to the technology. So moving on, how do classify these nanomaterials. So now we have looked upon the history, this the commonly available nanomaterials in the domain or otherwise a market, which dominates over the other for what property, and classification. So classification of nanomaterials can be based upon two things. One such thing based upon the material. So you can say that, okay, very vaguely you can say it as, no sir, it is based upon the material, metal or organic or inorganic or whatever the materials, or otherwise based upon the dimension. So what dimension you need, whether it is 0 dimension, 1 dimension, 2 dimension or 3 dimension. So 3 dimension is nothing but 3 phase, whether all are there in the nanoscale. If it is of 2 dimension, whether both the dimensions are there in nanoscale, or if it's 1 dimension, again what are those, and then what are 0 dimension. Otherwise, in detail, if you want to have a look, then you can classify this as based upon the dimensions, based upon the morphology. What is the what is the surface morphology that it has? What is the morphology that it has is on its surface? Is it flat? Is it sphere? Is it, what does it, how much roughness it has it onto the surface is one such thing. And then when it comes to aspect ratio, it has high aspect ratio as well as low aspect ratio. So with respect to high aspect ratio, nanowires and then nano zigzags are some of the examples. So we will just stick to the morphology. What kind of surface that you need, that is one such thing. The state, what kind of state that you need, whether it is isometric, homogeneous, dispersed suspension, agglomerated suspensions. As I have already said, that whether you need the particles to get bigger and bigger over the period of time, or you need particles to remain as such stable particles in the system, which should not react with any other thing. So you need to have a particle, a core particle over the top. You have a cap over it so that it doesn't react with the other particles. And chemical composition. So based upon the composition of the material or the nanomaterial, what is the composition that it has? So it can be single constituent nanoparticles. So as I have said, that it is not no composite, only one single metal, say example silver nanoparticle. Composites. So again, say AU, AG, or otherwise other combinations. Organic and inorganic. There are very huge number of examples that are there. Carbonaceous nanomaterials, metallic, quantum dots, ceramic, semiconductor, polymeric, nanogels, core shell nanomaterials. So when it comes to 0 dimension, it is nothing but the solid nanoparticles. 1D, the examples are nothing but nanorods. 2D, it is nothing but sheet layer. It has 2 dimension, and 3D is nothing but having a 3 dimension based on the dimension. Here you can just have a look about the examples that has been given. So moving on. So again, with respect to who gave what, that is one such thing, how it has been classified from when on. So nanomaterials are categorized according to their dimensions. So what is their dimension? And then what is the scale of that dimension? Whether it is, again, if you have 1 dimension or 2 dimension, again, if their scale is greater than 100 nanometer, are they really nanomaterial? Morphology, what is their surface morphology? The state, in what state? As I have already mentioned, that here you can say whether it is isometric, homogeneous, dispersed state, or otherwise agglomerated state, and chemical composition. So these, under these things, under these 4 categories, these nanomaterials have been classified or categorized. The first classification of idea was popped up in his mind. The gentleman's name is Glitier. So his scheme was mainly on the basis of crystalline forms and chemical composition. So okay, let us go with only the crystalline forms. And his way of categorizing or classifying the nanomaterials did not include the dimensions that the particle possesses or the material possesses. So in the year around 1995 to 2000, he said that nanostructured materials, basic concepts, and microstructure. So how does this classification needs to be done? So moving on, in the year 2007, these two scientists gave the scheme, such as the dimension also needs to come into picture. So that means that 0, 1, 2, 3 nanostructured materials were also included for the classifying them as nanomaterials. Classified various kinds of nanomaterials, nanostructures, using the dimensionality of the nanostructure itself and their components. So in this paper, they gave about, in the year 2007, in this paper, they gave about the justification of why and how these dimensions needs to be kept as one such parameter. So, so moving on, so the classification according to them was classified mainly on 4 different types with respect to dimensions. So that is 0D, 1D, D stands for dimension, 2D is nothing but the 2-dimension, 3D is nothing but the 3-dimension. And then at the bottom, the examples have been listed: solid nanoparticles, nanorods, sheets, and then pillars. So again, with respect to solid, and then hollow, nanowires, fibers, and then carbon nanotubes, films, patented surfaces, coatings, and then were some of the examples for the each dimension. So we will be looking into all these. So classification of nanomaterials: one is 0D, is nothing but spheres and clusters. 1D, one dimension, is nothing but a fiber or wire or a rod. So be it a nanorod or nanowire or nanofiber. 2D is nothing but films, two different surfaces. Again, how thick are the film plates and networks. 3D is nothing but you have 3 dimensions, and then how big is the landscape. So 0 dimension, when you look about the dimensions, otherwise as a huge thing. So 0D includes the spherical nanometers such as cubes, nanorods, polygon, hollow sphere, metal, and core shell nanomaterials, as well as quantum dots. These materials have dimensions less than 100 nanometer. Their length equals their width. So whatever the length that they have is equal to their width. So generally 0 dimension nanoparticles can be amorphous or crystalline in nature, single crystalline or polycrystalline, single or multi-chemical elements, and exhibit various shapes. So again, this, as it is being engineered, you can have a wide combination of all these properties. 1-dimension nanoparticles, so they will be having, as we have already seen, that nanofiber, nanofibers, nanowire or nanorods are some of the examples. Nanotubes, we call them. So 2 dimensions, wherein which the length is larger than that of their width. So this is one such way that we classify in 1-dimensional. 1 dimension not in scale, while the other dimensions are in nanoscale. Electrons are confined within 2 dimensions, and hence the electrons cannot move freely in their system. So this is one such big thing that you need to note. Electrons are confined only in 2 dimensions. They are arranged in such a way that they can't move in the system. So 2-dimensional nanoparticles, they include nanosheets, nanofilms, and nanoribbons. One dimension in nanoscale, while the other 2 are there, or other dimension will not be there in the nanoscale. Electrons are confined with 1 dimension, indicating electrons that cannot move freely within this dimension. And then it can be amorphous, it can be crystalline, it can be composed of metallic, ceramic, all polymeric matrices. Moving on, the 3-dimensional nanoparticles, they include nanophase materials consisting of equaxed nanometer and nanometer sized grains. The 3D nanostructures are not confined to the nanoscale in all dimensions, and they are generally known as bulk nanomaterials. 3D nanomaterials have 3 arbitrary dimensions beyond. So if the 2 dimensions are more than the nanoscale, so that also falls into 3D. In 3D nanomaterial, the electrons are fully delocalized, indicating all electrons will move freely within all 3 dimensions. So now, with respect to the dimension, it has been understood that it can be played with respect to 0, 1D, 2D, and 3D. So with respect to the materials, based upon the materials, so here we can able to classify them as carbon-based nanomaterials. Carbon-based nanomaterial consists of carbon nanotubes, fullerenes with a diameter ranging from 1 to 4 nanometer, very small. These are being synthesized for specific purposes, and carbon nanotubes are used in microelectronics, medicine, hydrogen fuel cell, whatnot. The upcoming technologies, carbon nanoparticles or nanotubes are also being used. Graphene oxide, an oxidation derivative of graphene, again, as like the metal oxide, is considered as a recently developed nanomaterial that is most attractive for use in biomedical applications. So even carbon has also been used in medical biomedicine or nanomedicine range. And then graphene is being now used for its electrical as well as optical and medical properties. So metal-based nanomaterials, as I have already said, nanomaterials such as gold, iron, silver, and other metallic nanomaterials or nanoparticles can be synthesized from the metals. They exist in 0 valence state, and their crystal structure is generally free of defects. They don't have any defects onto the surface. Metal nanomaterials have unusual better properties such as chemical, optical, electrical compared to their bulk materials. So you remember this this bulk materials, we will be discussing them in detail. So in a later stage, when we synthesize about the nanomaterial, how to synthesize the nanomaterial. And widely used in electronics, water remediation and treatment. The zero valence state makes them highly reactive, and most nanoparticles readily form an oxidized surface layer when they come in contact with air. So again, silver getting oxidized to its oxidized form, or otherwise titanium. So better when they are there in the oxidized form, how do they react? As I have already said that this statement helps them to zero valence state, makes them highly reactive, and most nanoparticles readily form an oxidized surface layer when they come in contact with the air. This is one such example, silver. If you open it in silver oxide, bimetallic or otherwise nanocomposites, you arrange the two different available metals in a structured manner, so that you have their unique properties which will be applied to your need. So composed of two metal components that exhibit unique properties such as chemical stability and reactivity, along with size dependent electrical and optical properties. So composite nanoparticles are solid materials consisting of several phases, with one of the phase having dimension of less than 100, or structures having nanoscale repetition distance between phases. So again, how are they arranged is the major thing. That still that can be, there are different ways to, or different pathways to place the atoms or molecules in the manner that which it is being designated for. The combination of several materials forming a composite is capable of producing different properties such as a good flexural strength, water absorption, again optical properties, wear and tear resistance or retention. So nanomaterials versus the bulk material. So this bulk material is one such thing, that the terminology that we use, where the particles have their size above 100 nanometer in all the dimensions. So be it 0, 1, 2, or 3 dimension, all the dimension with respect to dimensions, they have their size greater than 0. And then they can be seen easily through the microscope technique, or otherwise with the help of any microscope, you can be able to see them, or through a naked eye. As the particles are very big in nature, still you can able to. Low surface to volume ratio leads to better performance such as catalysis, solar wheels, and gas sensors. So this is one such good thing. Again, why we are discussing about the bulk materials is that from the bulk materials, nanomaterial can be synthesized. So we have seen the classification. Now with respect to the synthesis part, how does this nanomaterials get synthesized? As we know that nanomaterial will not be able to see through eyes, but bulk materials can be seen through. So you have a large surface area to volume aspect ratio leads to better performance, but here you have a low surface to volume area and high percentage of atoms of the surface leads to unique properties, whereas low percentage of atoms, you have a comparatively okay properties. With respect to nanomaterials, here you have been fabricated in such a way based upon your needs. Surface forces are very important. Again, surface forces, when it comes to surface force, what is the charge or the surface charge that the particle possesses? So whether it is negatively charged or positively charged, or you don't want anything to react, or otherwise you cap the nanomaterials. So that is one such thing. Surface forces are more important. With respect to bulk forces are not as important as surface forces. As a particle is big, you don't think more about it. The surface charge, again, there will be two different. In order to make the particle near to near, then again you need to compress the repulsive force and then make them attractive. There would be two different forces that will be acting upon, one van der Waals force and then electrostatic force. Repulsive and attractive force, where you would be compressing the electrical double layer and making the particles near to near so that they aggregate. So only the surface force are more important. Metal nanoparticles have unique scattering properties. So again, if you could able to recollect the ancient Roman thing, silver, Au, combination of nanoparticles which has been applied onto a glass vessel. So again, optical properties. Metal bulk have nominal or normal scattering properties. The semiconductor nanoparticles exhibit a very good energy retention. So again, that has been used widely, and the nanomaterials can be tuned by varying the size of particles. As I have already mentioned, that size specific, shape specific nanoparticles that falls under engineering nanomaterials can be synthesized. based upon different methods. So we will be looking into it. So for that, bulk materials is needed. With respect to bulk material, the chemical and physical property cannot be tuned. Nanomaterials complexity offers a variety of functions to products. Absorption and absorption of molecules are high. The particles getting onto, because of its high surface area, the pollutant can get onto the surface of the nanomaterial. So that is one such thing. And then examples of these nanomaterials can be from carbon, silica, AU, AG, or titanium dioxide, anything. And then examples of this bulk materials includes sand, cement, alumina, iron ore, or any salts, even the salt, the table salt that we have. So there are slight differences between the nanomaterials and bulk materials, but one such significant thing that we will be looking with respect to the bulk materials is that how these nanomaterials can be synthesized from the bulk material. So next thing that we will be looking into is the synthesis aspect of nanomaterials. Yeah. So as we have seen about the synthesis aspect, so there are two different approaches. One is bottom-up approach and then top-to-bottom approach. Top to bottom, so top to you can say top-down and bottom-up approach. So top-down is nothing but you have a bigger particle and then making them into very small particles. Assume that you have a ball mill. Ball mill nothing but a circular drum where you add stones and then you introduce steel balls and then you switch on the drum. It keeps rotating for one day, and then the rock will get converted as a fine grained particles. I'm using the terminology called fine grained particles. I'm not using nanomaterials. Finely tuned particles. Normally the rock would be of very big in size, but when you keep on using the ball mill, reducing the size, and then you will be having fine grain in micron size. Or if you keep on still using the ball mill, you will have a very fine tune of nanomaterials. So this approach is nothing but top-down approach. From the bulk materials, from the bigger material, you arrive at the nanoscale level. Bottom-up approach is nothing but building materials atom by atom, that is from the very minute particles, again deriving to the from the atom level to the nanoparticle level. So chemical reduction is mostly used technique. Biological method of nanoparticle synthesis is also categorized under bottom-up approach, where biomolecules incorporate with metallic substances for nanoscale material production. So top-down approach, this is one such thing. With a physical way you can be able to synthesize the nanoparticles. Again, electricity will go in, and then the way the time taken, you will not be able to have the control over the size, surface, as well as the dimension of this. But still, this is also one such method where you can be able to synthesize nanomaterials or nanoparticles. The physical technique of nanoparticle synthesizing has advantages as it avoids nanoparticle solvent contamination, but it is not negligible to consume a large quantity, as I mentioned, electricity for condensation and evaporation of particles. So again, if you look for evaporation and condensation process, this is one such advantage or disadvantage you can say. Furthermore, highly elevated temperature and pressure modulations will create longer time for nanoparticle manufacturing, indirectly expense the cost of synthesis of nanoparticles. So as I gave the example of ball mill, so it takes a longer time for synthesizing the nanomaterials. Bottom-up approach in the chemical method. So there are different methods that are there. There are scientists have explored since 2007 or late 2000s. The scientists or researchers have explored into these two approaches in all the verticals. So be it from the plant, be it from the extracts, be it from the oils, be it from the different solvents. So all these pathways have been explored to synthesize the nanoparticle. Even there is a terminology called green chemistry, where you synthesize nanoparticles in a green manner. So again, in this one such method is chemical method, in order to synthesize high purity and stable nanoparticles. Stable, again, the surface charge comes into picture. Whether if you want to have a stable nanoparticle, either you need to think about the charge in which the nanoparticle will have. Reducing agents and protective agents are used to synthesize nanoparticle and avoid agglomeration. Agglomeration is nothing but the particle getting bigger. strong chemical consumption leads the synthesized nanoparticle to be contaminated. Assume that you want the particle not to get bigger in size. You want the particle to stay in 10 nanometer itself. Assume that the particle is being synthesized for 10 nanometer, and then you need to cap the nanomaterial so that it doesn't get accelerometer. Again, one such capping agent, again, different chemicals are being used. Although the response is fast and cost effective compared to physical technique, it is hard to regulate the variation of nanoparticle size, shape without significant reduction in stabilization. With chemicals, you will be able to attain size-specific nanomaterials or nanoparticles, but without chemicals, it's not possible. So mostly chemical methods are used. They elevate the temperature. Again, there is a factor that comes with respect to the usage of different chemicals, solvents, and then high temperature. So among the various available methods that are there in the synthesis approaches, so I picked up only two things, and then I will be giving you a very simple example, because scientists have come up, as I have said, that even in plant extracts, scientists have communicated and confirmed the synthesis route of nanomaterials. So discussing all of them in detail within an hour to the audience will be very hectic. So I have picked two different methods for top-down approach and then bottom-up approach. So one such thing is mechanical milling, where you have the bigger particle and then making them into small. Even the salt, the table salt that we use, if you keep reducing their, if you with the help of ball mill or otherwise, if you keep reducing their size, you get a nano size salt. Okay. Mechanical milling is a cost-effective method for producing materials at the nanoscale level from bulk materials. Again, we have seen what is the properties of bulk material versus the nanomaterial, how they are good at it, and then how nanomaterial outperforms the bulk material. It is helpful for production of nanocomposites. If naturally available bulk material is there, then you can go for, you can also yield nanocomposites. And then one more technique in laser ablation is nothing, and top-down approach is nothing but laser ablation. This synthesis involves nanoparticle generation using a powerful laser beam that hits the target material. So again, with the help of high power laser beam, you could able to churn out nanomaterials at a very, very small level or in the nanoscale level. During the laser ablation process, the source material or precursor vaporizes due to high energy of the laser irradiation, resulting in nanoparticle. Because of the high energy that you pass on to a membrane, so or otherwise a plate, so you yield nanomaterials. Wide range of nanomaterials can be produced or fabricated or synthesized, such as metal oxide, metal nanoparticles, carbon oxide composites, and ceramic nanomaterials. Bottom-up approach. So as I have already said that there was a message in the chat box. Fine. Moving on. So in the bottom-up approach, one such commonly available material that is being used is nothing but the sol gel method. The sol gel method is a wet chemical technique which is being extensively used. So again, solvent or gel. So there is a name for why this has been termed as sol gel, used for development of high-quality metal oxide nanomaterials. This method is called sol gel. During the synthesis of metal oxide nanoparticle, the liquid precursor, so that means that the liquid is transformed to a sol solution, and then the sol is ultimately converted into a structure that is called gel. So this we call it as sol gel method. So this is being widely used as one such method to synthesize nanomaterials or nanoparticles. The sol gel method is economically friendly and has other advantages, such as produced material being homogeneous in nature. That is one such thing. They are fine. The processing temperature below it is relatively low, and method being facile way to produce composites and complex nanostructure. In sol gel method, also researchers have went with high temperature, and then this is not common with respect to all the synthesis that has been done with respect to sol gel. Hydrothermal method, this is also one such approach, again from bottom up, where you arrange the atoms in such a way that this method is also being used extensively to synthesize nanomaterials. In hydrothermal method, nanostructured materials attained through a heterogeneous reaction carried out in an aqueous medium at high pressure and temperature around a critical point in a sealed vessel. So you apply pressure, temperature, and then you get nanoparticles out of it. So microwave assisted. So again, you all the reaction that happens in the microwave environment, assisted hydrothermal method have recently garnered much more attention than the hydrothermal methods for its synthesis results based upon because of its high efficiency as well as for the merit. It can have the merits of both hydrothermal and microwave. It can have a very good, you can have a very good nanoparticle coming out from the system. So moving on, characterization of nanomaterials. So as I have mentioned earlier, so there are different methods. So at this point of time, giving an overview about all the methods for the nanomaterial synthesis will not be a proper justification that can be done to the audience. But at the same time, if you know, if the audience can able to understand that these are the two bases in which the nanomaterials are synthesized, then it would be great. So moving on, classification of nanomaterials. So characterization of nanomaterials. How does this nanomaterials gets characterized? So on what basis do you characterize? What do you need? Actually, as we say that, so we have seen classified based upon the dimensions and then state, surface, and then surface charge, and then everything. So we have come across these terms in the past in the lecture, and then all these will be characterized. So is it possible? Yes, we need to do that. Then only it is possible. And then when it comes to structural characterization, so how does the structure of the material looks, whether it is spherical in nature, or is it a rod or tubes or fibers or otherwise, how do they look? And then for that, you take the help of scanning electron microscope. As the name itself suggests, that you scan the layer of, you apply the nanomaterial over the grid, and then you scan the surface. So that will give you how does this nanoparticles are. And transmission electron microscopy, microscope, as the name itself suggests, that you allow the electron beam to pass through the sample and then get the shape. And then in both SEM as well as TEM, this is one such widely used character, or otherwise a basic characterization technique that you can think about it, because of the fact that you can relate in all the journals that is being out in the scientific domain. And surface structure, tunneling microscope, tunneling microscope is also being used for to determine the structure of surface of the nanomaterials. And surface topography, how to know the morphology that we were discussing about, how is the surface, as we have gave the example of flat or anything. So here, how is the surface of the nanomaterial? Is it very smooth enough, or what is the depth, or otherwise is there any other defect onto the surface, is one such thing that you need to look upon. For that, apart from scanning electron microscopy, it is AFM will give the better results, that is atomic force microscope, that will give you a better results, and then it will give you the values in 3 dimension, where you will know how good is the sample. And microstructures such as HRTEM, high resolution, in the transmission electron microscopy itself, you have a very good resolution type, where you can fine tune below 50 nanometers, 100 nanometers. Raman is one such spectroscopy where you can also able to arrive at the structure. Composition, how is this composed of? And then apart from this, there is other methods such as XRD also gives you the size as well as the crystalline state structure of how good it is. Even now the softwares are available with respect to the XRD, where it will also tell you what is the crystalline nature of the sample. Compositional characterization, how to know what is the composition that the nanoparticle has. So again, TEM, or otherwise HR-TEM combined with EDX, energy dispersive X-ray, will help you out in arriving at the composition. What is the composition? Or otherwise, X-ray fluorescence will also help you out in knowing at the bulk composition, also at the impurities that is being present. All these chemical methods, when you do it, so you will be having trace elements of impurities into the synthesis result, or otherwise the nanoparticles. How what is the percentage composition of these impurities, or otherwise what is the composition of each and every metal that you have when you go for metal composites. Surface composition, again, XPS is one such method, and then mass spectroscopy for bulk composition is also one such method that will go for composition characterization. NMR is nuclear, microwave resonance is also one such technique where you will be having the composition. So again, it depends upon what exactly you need. If you are very specific about the size, then you can go with the other base. And then size, again, when it comes to size, what is the size that you're talking about? Whether the size is there in a powder form or whether the size that you wanted there in the liquid form. Again, those are the two things that you need to look upon. If you are looking about whatever the structure composition, the size that you arrive in from XRD or from TEM, XRD, there is a separate calculation. It will not give you exactly the size of the nanomaterials, but still there is a back calculation which you can able to do and then arrive at the size. Whereas at TEM, and then it is in the powder form, and then when you suspend the nanomaterials in the suspension liquid, again the size changes because of there will be a thin layer of water that will be surrounding, and then we call it as hydrodynamic diameter. That again, if you want to characterize it, then again it will have its own way of characterization, where dynamic light scattering, again the principle of spectroscopy will be applicable, and then you pass on a laser beam in a cell and then arrive at the hydrodynamic diameter of that nanomaterial. So moving on, the scanning electron microscope, as I have mentioned that it's one of the most widely used techniques or commonly adopted techniques in order to characterize the nanomaterials. So this will give you information about the surface as well as the chemical composition. Again, SEM combined with EDX will give you the chemical composition. And then transmission electron microscope, it uses an electron beam to image the nanoparticle sample. Again, the nano beam passes through the sample, and then this is one such high-end instrument where you need a sophisticated facility or otherwise an arrangement to carry out or to arrive at the size of the nanomaterial. But still, it is very efficient in determining the size, shape, as well as the size distribution. Again, a size distribution, you need to sit for a long time in order to know the size distribution. Again, the morphology, as I have said, that combined with EDH, it will give you the composition as well. So these are some of the pictures that are available in the scientific reports or the journals, where if you could able to, they have gone with respect to 10 nanometer level, or this will give you the best example of 5 nanometer. So how does this synthesized nanoparticle looks under 10? So that is again one such thing. And then with respect to this scale denotes the scale in which you are magnifying it, and then be it the 200 nanometer or 500 nanometer or 10 nanometer resolution. And then Fourier transform infrared spectroscopy. Again, this is also one such microscopic technique where we call it in the short form as FTIR, enables the in situ analysis of interfaces to investigate the surface absorption of functional group on nanocomposite. So again, this is also one such a technique where you will be able to arrive at the morphology of the material that you have synthesized. So Raman is again, this will also give you the structural morphology of the nanomaterial used. Otherwise, if you are not very much sure, or otherwise if you are not focused about the surface morphology, then mostly researchers would be restricting themselves with respect to the compositional, or otherwise the percentage of impurities, the size and shape of the nanomaterials. Infrared spectra, again, the chemical composition and the bonding arrangement of the materials that have been synthesized will be obtained. And then IR helps in arriving at the structure of the nanomaterials as well as the functional group. Again, if you go for the other nanomaterials with the functional group attached onto its surface for a specific purpose, then again, this will help you. And nuclear magnetic resonance is one such thing, where this will give you the structure, the composition, purity, and what is the change that the nanoparticle has undergone. So again, it depends upon though the nanomaterial has been characterized, it doesn't mean that all these characterization technique needs to be taken into consideration, but it is upon the individual to decide upon what they or he or she is interested to know about from the synthesis. Either they are very specific about the size or shape, or otherwise the surface. So X-ray photoelectron, we call it as X-ray fluorescence, XFS or XPS is also one such technique where you will be able to arrive at elemental and chemical composition at the surface of the nanomaterials. So atomic force microscope is one such, as I have already said, that the surface perfections, imperfections can be able to arrive at with respect to the AFM. The surface roughness can also be able to arrive at it. And then as mentioned earlier, so this is dynamic light scattering is one such technique where it is adopted to determine the size of nanoparticles in the suspension, in the liquid. So that is being denoted as hydrodynamic diameter, and then that it can be done with respect to dynamic light scattering. So as nanoparticles are being used widely in different domains, I have not highlighted dynamic light scattering, but still that is also being used when these nanoparticles are added into water. So this is how the AFM results looks. So again, it will give you the structural imperfections that are there onto the surface, how uneven the surfaces are. And then overall characterization, as I have already said, that X-ray diffraction will also help you out, not directly with respect to the results, but also the size you can able to confirm with respect to the TEM, or otherwise you can correlate with respect to the TEM. So with this, I will stop for today's lecture. And if any queries are there, then we can discuss. Otherwise, you can drop out a message in the chat box so that we can discuss in this session. Yeah, any questions? It can be left in the chat box. Okay, thank you. Please provide all PPTs to all the participants of online course. I will check with the GIAN office. This is my first program. I'll check and then I'll get back to you, Mr. Subhash Chandra. Yeah. So if there is no specific query, still you can able to get back to us with respect to the same. If you have any queries, and then you can drop us a message that will be addressed back to you.
Good morning,
so
sir.
This, yeah.
This is Bhagya Lakshmi.
Please tell.
This is a very excellent talk. This is very eye-opening talk. Sir, in that, to study the morphological characteristics in this, is there any lecture is there to interpret, how to interpret? We are getting the results, right, sir? For journal writing and all. Still, we need some inputs, how to interpret that, what are the outputs?
Okay, there. So you have, you have, you want to know what does the result mean, if I'm not wrong, right? Yeah. It depends upon, as of now, if I could able to, if I'm not wrong, there is no such lecture that has been planned, but still that can be, if that is the, you may know what technique that you use, that you had, is it XRD or NMR
XRD,
or
SEM analysis, and then FT, and the Fourier transform. That FT, in this.
Where
after getting the result, what are the important thing highlights? We can get it from that.
From XRD, from XRD you can get the crystalline nature. Most of the places where you do the XRD analysis, they have a software coming along with the system, where they will let you know based upon the peaks that you get from the graph, that you will be having the powder sample mounted onto a capsule, and then you will be having peaks, and then based upon the peaks, You can, from the software, you will be able to know what is the material that you have synthesized. That is point number one. And then based upon the peaks, also you can able, there is a formula where you can able to, based upon the peaks, I could not able to get the exact formula right now. D by
sir, can you spare some one session? Sir, can you spare one session, maybe some half an hour, to discuss on this? I'm requesting you, if there is in your schedule, if it is not there also, you can, if possible, please consider that.
Okay.
You take some journals, that output, this is the output. From this, we are interpreting in that way only. Like that, show some examples and then give.
I can help you out for XRD. I have knowledge about XRD. And SEM and TEM, again, it is again SEM and TEM, it is about the size and shape. That is one such thing. Because when it comes to size, more we prefer with respect to HRTEM, where you will be having a very good picture about the size and then the shape of nanomaterials, particles. And then these are the things which are commonly used. I think. So I can help you out.
Also, okay, sir. XRD also, sir. Okay, sir. I can get from the GIAN course. Okay, XRD, how to interpret that, I can get it. That is also good for me.
As of now, we don't have any lectures planned upon that. As I mentioned that I'm from environmental background, and then but I will do justice to the question that you have asked in this 5 days, and then if not, also I will be able to be in touch with you and then get it.
Okay, sir. Sure. Thank you, sir. Thank you.
Good afternoon, sir.
Good afternoon.
I wanted to know that in XRD analysis, how we can found JPDS file for particular nanomaterials.
Come back again, Subhash.
Sir, how we can found JCPDS file for a particular nanomaterial in XRD analysis.
JCPDS file that comes along with the system itself, I feel. Otherwise, it comes along with the instrument, if I am not wrong. This is how I did the analysis, or I have the exposure with respect to the JCPDS file. So I think there is no cracked version available. But if you can be able to check with the agency that you have done the XRD analysis, then you will be able to get the JCPDS file. They will not be sharing with all the people who come and do the analysis, but still, I think they would be giving you the values.
Okay, thank you.
Okay, what is the better technique, top down or bottom up approach? As I have said that it is all depend upon the nature or the requirement of each and every method has its own advantage as well as disadvantage. Be it if you want, most of the synthesis are targeted with respect to size. So mostly we can go with chemical, where you have better control over the arrangement of atoms than the physical method, than the top down. But still, one such example is sol gel method, and then where you will be having a better control, and then whatever the nanomaterial that you prepare or otherwise fabricate, synthesize, will have a very good size component coming into picture if you are very size centric, or otherwise if you want to shape centric. I need to check and then I will get back to you with respect to shape centric synthesis of nanomaterials. So
So next session is 2 to 3 answers.
Yes. The next session will be Professor Hadas. She will be taking the lead, and then followed by Dr. Ram. So the session will start at 2 o'clock, and then because of the inaugural session, we had a slight delay in the first session, but I think from afternoon session it will be dot on time. So you can start logging it from 1:55.
Thank you.
It's at 2:30, I think, the next session.
Just a minute. I'll just check Professor Hadas.
In the
Professor
schedule,
Hadas,
4 to
it is
4 to 3?
today's schedule is at 2 o'clock. 2 o'clock.
Okay, thank you.
Yeah. Okay, thank you all. So let us meet at 1:55 dot on time. Thank you.
Thank you, sir.